So one of the things I always do is warn you that you should always follow the local electrical codes. If none exist, then follow the USA National Electrical Codes known as the NEC. Make sure that what you're doing is electrically safe. And the ARRL actually recommends that you vacate your shack during lightning storms. And that's a fairly good idea. As for questions, I ask that you hold questions till the end. For one reason, what I found in past presentations is that whatever questions are asked, I'm going to answer in 1 to 2 slides anyway. So hold your questions. And the other thing is, I've pretty much lost my hearing, so I can't hear very well. So that helps keep things going faster by holding questions till the end. Okay, so typically a lightning strike is 3 to 4 pulses per strike, 10 to 170 microseconds total. The first pulse averages about 18 kiloamps, and 98% falling between 3 kiloamps and 140 kiloamps. So they're pretty exciting currents. Subsequent pulses, as they occur, do drop to about half the current. The Dayton area, I realize some of you are not in the Dayton area, we have about 50 thunderstorms a year. So if you have a 75-foot tower, you're likely to take a 1 strike per year. And that's out of the GE Technical Training Manual. For this presentation, any math that I do, I'm going to keep it simple and just use 10 kiloamps for the strike energy and a 10 microsecond rise time. And NASA actually determined that some of the lightning strikes they measured from spacecraft actually showed that the energy goes all the way up through gamma rays. So it's basically DC through gamma rays. Okay, so how I learned the hard way was, in 1984, I built a house, and the builder was really friendly. Before I built the house, I said, hey, can I put a tower in this neighborhood, and so on. He said, yeah, in fact, I'll even dig the hole and pour the concrete for you, which he did. And so once the hole was dug, we were over there looking at the construction progress, and the one neighbor walked over and he looked at the hole and he said, you putting up a tower? I said, yeah. He said, are you a ham radio operator? I said, yeah. About then I started getting really nervous. and he said, that's great. It wasn't quite the response I was expecting. And he said, yeah, he says, your lot gets hit by lightning almost every year, and the house over there lost its chimney, and the house over there got almost burnt down, and this house had some other issue. He said, you're putting up a lightning rod. We don't have to worry about that anymore. And I thought, okay. And so he was right. For the first 7 years, I kept taking direct strikes to the tower, and I had damage every time. And about that point in time, I found out that Polyphaser published a book on lightning protection. So I purchased that book, and I implemented everything they said, and I had no more damage the rest of the time we lived there. So that's where all this information came from. And so I always ask, well, what's the damage? Is it voltage or current? And the answer is both. And the current being the worst of the two, because it can burn things up and destroy wires and do all kinds of nasty stuff. And the current also actually creates voltage, because you have current flowing through a resistance. It creates a parasitic voltage. And I should mention, this session is apparently being live streamed. It'll be available on YouTube later on, I guess. And so anyway, so if you look at current through a voltage, if you have a 10 kiloamp lightning surge, a 1 ohm resistance, you'll have 10 kilovolts across it. So you need to keep your resistances in the lightning's path to a very low amount. If you happen to have an inductor, then the 10,000 amps at 10 microseconds will develop 150,000 volts across that inductance. So one of the things I like to explain is the thing that really damages a circuit is voltage difference. Like if you look at the simple little transistor, if you put too much voltage from collector to emitter, it's going to pop. So the whole tent to lightning protection is keeping the voltage differences to a bare minimum and within the ratings of the parts. And this is, if you look at old school, this is how a typical house was grounded, especially if it's old construction. I mean, if your house was built before like 1980, this is the way it was built. To add to that, typically what happens is, a house is built, you bring the electric in, you bring the phone in, they're brought in at different locations typically. Then you added cable TV and external antennas, and they come in at some other location on the house. So you end up with something that looks like this. And that's the worst thing you can do. And by National Electrical Code, this is what should have been done. So I'm willing to bet that 90% of the houses today are configured the way that previous screen was. There's very few actually configured the way this shows. So this is the way you want your house to be grounded. You want everything bonded together. You really would prefer to have them come in at one location. A little bit more on that in a few minutes. And like I say, the single entry point with bonding is probably one of the most important things you can do to stop damage. And this is an example. This is out of Ward Silver's book, and out of the ARRL. And but anyway, this is the single point grounding. This is what in a case like this, if you follow the lightning path through the system, there's no real reason for the lightning to go all the way up to your radio and come back out. It's just going to hit that panel and go right down to ground. So yeah, the radio may float up to some high voltage, but the whole radio is at the same potential, so there's no damage. And this is another example of how you can do that. And resistance can be both a friend and an enemy. From a reducing current, higher resistance is good, but from getting lightning to the ground, you want lower resistance. And so it sort of boils down to Ohm's law, except where you have to take inductance into consideration as well. And for example, a half-inch coax about 100 feet long is 51 microhenries. Tower is approximately 5 microhenries per 10 foot, and tower joints are 0.001 ohms typically. This is, by the way, all the links in this presentation, if you send me an email, I'll send you a copy of the presentation. That way you can just click on the links. And my email address, just use my call sign at arrl.net. And these are typical soil resistances you will see across the country. And you can see there's quite a range for soil resistance. And once again, higher resistance is bad from controlling the lightning. The National Electrical Code wants your resistance to ground to be less than 25 ohms. And Motorola likes it to be below 10 ohms. Typical telecom switch is under 2 ohms. And Verizon likes to see the ground resistance being less than 5 ohms. And to calculate ground resistance, this is out of the military handbook. And so if your soil resistance is 5,000 ohms, then your resistance to earth is 20.6 ohms. And if it's 2,500 ohms, then your resistance to earth is 10.34. But if you're pushing 10,000 amps through that resistance, that's a lot of voltage. So if your soil resistance is 100 ohms, then it's the ground resistance is 0.41. And if you have one ground rod at 0.41 ohms with a 10 kiloamp current surge, the bottom of the tower is at 4,135 volts. Now, if you do have 3 ground rods, one on each leg, now you're down to 0.14 ohms, and you're down to 1,300 volts. And keep in mind that's at the tower leg, and the top of the ground rod will be at a higher voltage. So these are some things you can do to improve grounding. You've got to have at least one ground rod on every leg. That's, as far as I'm concerned, that's bare minimum. It's much better if you do like this one on the right, where the wire goes out some distance and you put another ground rod in, you go out some more distance and drop another ground rod. And typically, if a ground rod is 8 foot, the next ground rod should be out 16 feet. If you use a 10-foot ground rod, the next one's out 20 feet. So the length of the ground rod affects that. The one on the left is probably typical of what you might see for a communications tower for a cell phone, something like that. It's for ham radio, so I've probably never seen anybody do this, but they've got a loop going around the house. In my case, my current loop goes about 2/3 of the house. There's no easy way for me to get around the front to complete the loop. These are, I don't know how well you can see this. In this case, the people tried to be, on the pictures on the left, the people tried to be really neat, and they got lots of 90-degree angles in there. Well, all of those are inductors, and that's bad news from a lightning strike. The tower on the left, they have one ground rod on it. And let's see, we got, here's some calculations. Here's the calculations. With the way that tower was done on the right, it's about 900,000 volts to the ground. This is another example of tower grounding, and I would consider this basically to be the bare minimum. And then the question comes up, what gauge wire should I use? Well, the NEC recommends 10 gauge and 14 gauge. And I looked at that, I said, you got to be kidding. Why would you use such light gauge wire? But there's a reason for that. Polyphaser recommends the use of 10 gauge. Ward Silver recommends 6 gauge or 2 gauge. Motorola recommends 6 gauge. Mike Holt says 6 gauge. My local power company uses 6 gauge. And I currently use 4 gauge. And I've been using stranded, but I bounce back and forth between solid and stranded. Stranded tends to have more surface area, so it's a little bit better resistance. But then you got corrosion and other things getting in the way. And you need to consider skin effect and inductance. So like they sell the strip copper, that's by far the best thing to use because you got tons of surface area. Al Torres used to put content into this presentation, actually gave the presentation himself a few times. He put together what he likes to do is he likes to take old Romex and pull the 3 wires out of it, twist the 3 wires together, and use that for ground wires. That's not a bad idea if you need to use some, you got some old AC wires hanging around. Al generated this chart, and if you look at 14 gauge there on the left, it can handle 187 kiloamp for 10 microseconds without the wire melting. And so that's why the NEC uses the 14 gauges, because it can handle that. The catch being is if you had multiple strikes fairly quick, you'd be in trouble. But that's extremely rare to happen. For protection, if I can get away with it, I use quarter wave shorting stubs. You can make them yourself, or there's companies that sell them. So like the 450 or 440 repeater that I use a quarter wave shorting stub on that repeater. Quarter wave shorting stubs can take 100 kiloamp lightning strike and just laugh at it. It can handle 10 kiloamp strikes all day long and not care. So you don't have to worry about replacing arc devices inside the arresters. They just work. But if you got an antenna that's multi-band like HF or a dual band VHF, UHF, you can't use the shorty stubs. You got to use the standard lightning protectors. I use AC line protectors. I only use Triplite or SGL Weber. Triplite and SGL are both owned by Eaton nowadays. And I only use electrical strips that have been certified by an agency like UL, NEMCO, CSA, ETL, and some of the others. It helps ensure that you got a safe product. Now, the other thing I'll mention about Triplite is a lot of people look at the price of those things and say it's not worth it. The catch is they have RFI suppression in them. So they actually have ferrites in there. And so not only do they have a lightning surge protection, but they also have EMC filters to knock the RF down. They're rated 40 to 80 dB of isolation I think the 40 dB is down in the kilohertz range and the 80s up in the 6 meter band. And it's sort of a line between the two. I've been trying to get him to confirm that for me, but so far I haven't been successful. But anyway, not only does it provide lightning protection, but it also helps your computers and other such things from driving RF signals back through your power wires, which then get into your HF antennas. You should also have an AC line protector, surge protector at the service panel. Should be installed by a licensed electrician. All guide wires need to be grounded. And these are some examples of bonding. The picture on the left, once again, it's out of the ARL book, but the picture on the left is the way that my current house is set up. And the one on the right shows how to do things if your tower's out of distance. So one of the questions I get is, does it work? Well, you already heard that I never had any more damage after the first 7 years. But here's a picture of the power transformer my house is currently on. And you can see it's got a nice little black mark on the left. But what's a little bit more difficult to see is that it's been physically disconnected from the grid wire. The lightning strike was so powerful, it literally knocked it off the grid. And on the picture on the right, you can see the wires going to my house off the bottom right. And so I had 0 damage from that lightning strike. And I should mention on the triplet isobars, every cluster of equipment in my house has one. So the TV in our media room, everything's plugged into an isobar. The master bedroom, everything's plugged into an isobar. My radio bench, it's got an isobar on it, and everything's plugged into it. So it helps keep everything at the same potential. It's got the surge protection in it, and it's got the R5 filtering in it. So it helps keep the noise away from the radios. We've also been asked about the IC905. As far as if you read the information on the IC905, and if you look at the model number, ICOM never intended that to have antennas mounted on a tower. They meant for it to be a rover. And that's why it's got the 3-digit number instead of the 4-digit number. And if you look at all their ads, they always show it as a rover. But if you're going to mount it on a tower, then treat it as you would a mass-mounted preamp or a mesh Wi-Fi kind of unit. And there's on the bottom, on the right side, you can see a ground wire coming off of the upper unit going to ground. You need to get that tied to the tower. And so I would mount the RF unit on the mast as close to the top of the tower as I could. I'd run the ground wire from the ground terminal unit to the clamp on the mast. And the basic is to keep everything at the same voltage. Depending upon antennas, I might use a Nextech coax arrestor similar to the part number I have there. It's good to 12.5 gigahertz. I would also mount 2 Ethernet protectors, one at the top, one at the single point ground. That'll help keep lightning surge out of your Ethernet. And I listed a couple options for doing that, a couple of part numbers. And also follow the guidance in Ward's presentation. Okay, so a lot of the information out of this came out of the ARL handbook. Some of it came out of Polyphaser's book. And I've got, like I said, I've got links on these pages that you can go to that will have information. Mike Holt's got a really good page on national electrical codes. And Jim Besterfeld also has some pretty good information. And like these next one, all these links you can send me an email. I'll send you the presentation. That way you can just click on the links. And here's some more links. And then I wanted to say thanks to Ward Silver and Al Torres and the reviewers, John Monteith, Ward Silver, and Al Torres again. And like I said, my email address is my call sign at arl.net. I also stuck a couple cards down here if you want to just grab a card, and we can go from there.